I would love to say that this is the moment you've all been waiting for, but it probably isn't. But we're going to talk mass stoichiometry. We're going to break it into a couple of different parts. We're going to start with going from moles that we know to moles that we don't know. Okay, what is stoichiometry? In simplest form, stoichiometry is the mass relationships within a chemical reaction, which probably doesn't make a whole lot of sense, but we can also think of it as a scaling of a reaction. Now, instead of working with reactions right away, let's think about sandwiches, because, yeah, why not? If I take a sandwich, and this is the sandwich I'm going to make, where my recipe is 2 pieces of bread, 1.5 tomatoes, that's a lot of tomato, 4 pieces of bacon, then that makes my sandwich. And I can write it as a chemical reaction, and I can write it as a recipe. Now, if I am bound, absolutely stuck to that recipe, and I can't do anything else, then the next question becomes, what happens if I'm going to be making 5 sandwiches? What happens if I'm going to make 500 sandwiches, or I start up a sandwich business and I'm making 5,000 sandwiches? If the recipe is the same all the time, and I'm not slipping extra bacon in or like eating bacon on the side, then the recipe has to be exactly that every single time. And if I made 5 sandwiches, I do that entire recipe multiplied by 5. 5,000 would I take my recipe and multiply by 5,000. Stoichiometry is kind of that with a chemical reaction, just don't eat it. Now, often when we start with a chemical reaction, or where we're at right now, we would want to look at that chemical reaction and think about it in terms of 1 molecule of N2, nitrogen, reacts with 3 molecules of hydrogen, and they're going to make 2 molecules of NH3. And that's okay, but that's not very realistic, because we're never really going to have 1 molecule reacting 3 molecules. Not realistically. We're always going to have a container that has thousands, hundreds, billions of those molecules. So we need to scale up that reaction. And remember, we were talking about moles earlier. So we need to think about reactions in terms of moles as well. But let's start with counting molecules, because that's probably where we're comfortable. If I take that reaction again and I say, how many molecules of hydrogen would I need to in order to make 72 molecules of NH3? I take my sandwich recipe, and I want to make 500 sandwiches. How many tomatoes do I need? How many bread do I need? Or how much bread do I need? How much hydrogen would I need to make 72 molecules of NH3? Well, what I'm going to do is I'm going to take my recipe and I'm going to set up a ratio. So half of my ratio comes from the recipe, comes from the balanced chemical equation, and the other half comes from where I'm trying to scale it up to this other amount. And then I'm going to solve for x. And when I do the math, I end up with 108 molecules of hydrogen. And hopefully that makes complete sense, and hopefully you also did that on your own and not just took my word for it, but check my math. But what's important is I'm going to set up a ratio based on what I know and what I'm looking for, and I'm going to find out the other thing that I have. And guess what? That's pretty much a main part of stoichiometry. All right, let's talk about moles. I'm going to take that reaction, same reaction, and I'm going to read it differently. Not much differently, but a bit differently. I'm going to read it as 1 mole of nitrogen reacts with 3 moles of hydrogen to make 2 moles of NH3. Exactly the same reaction, exactly the same ratio, exactly the same numbers. Now I'm just talking about moles instead of molecules, but nothing else has changed. So now I could ask almost exactly the same question, except how many moles of hydrogen are needed to make 4.8 moles of NH3. The only thing that's really changed are 2 things. 1, I'm talking about moles. 2, it's not a nice round whole number anymore. It's a fraction or a decimal. But I'm going to do exactly the same thing. I'm going to take a ratio where half of the ratio comes from the balanced chemical equation, the recipe, and half of the equation comes from the things that I'm looking for, the new scaled up version. Instead of 2, I want to make 4.8. So what changes? Do exactly the same math in exactly the same way, and I end up with 7.2 moles of hydrogen. It's exactly the same as what we did before. It's just maybe a little bit less convenient because decimals. But decimals are our friends. Okay, we're going to try a couple more. I'm going to take exactly the same reaction, because why would I be creative? And I'm going to look at it slightly differently. I'm going to ask now, how many nitrogen do I need in order to react with 7.58 moles of hydrogen? It doesn't matter if I'm looking at left side to right side or both on the left side. So similar kind of thing. I'm going to have half of my ratio set up from the balanced chemical equation, the recipe. So 1 mole of nitrogen on top, 3 moles of hydrogen on the bottom, because that's what the balanced chemical reaction says. I can ignore the other stuff altogether. And then, well, what do I do if I have this different amount, 7.58? I'm going to do the math in a very similar way, and I'm going to get a very, well, I shouldn't say a very similar answer. I'm going to get an answer of 2.53. And again, please double check my math so that you push the buttons as well. This one I want you to try on your own. So pause the video so you can work this one out. I'll display the answer in a moment. Did you try it out? Did you pause the video? Okay, so if you did it, you set up a ratio and you ended up with 7.6 moles of oxygen. If you didn't, try it again. That's the answer. If you're still not sure, we'll talk about it first chance we get. Okay, at this point, you should be able to set up those ratios and you should be able to solve those ratios based on numbers of moles. Next time we're going to talk about the other pieces of stoichiometry because stoichiometry is going to end up being 3 steps in total. We've looked at one of them, but it's also step number 2, and it's the most important piece that we have. Talk to you another time.